In the previous video, we'd come up with a formula for AN, which I've written out here in blue, and AN is the area enclosed by the curve CN, and we're trying to show that the limit as n tends to infinity of AN is equal to 8 over 5 times A1. So we'll continue on and simplify this formula a bit more. So we can factor out the 3, which is inside the brackets here. So what we get then is AN is going to equal 3 times root 3 over 4 times s squared. And then in the brackets we're going to have 1 over 3 plus 1 over 9 plus 4 times 1 over 9 squared, and then plus 4 squared times 1 over 9 cubed, and that's going to continue on. So last term then is going to be plus 4 to the power of n minus 2 times 1 over 9 to the power of n minus 1. So we can see that the power of the 4 term is always 1 less than the power that we raise 1 over 9 to. So for example here it's 4 to the power of 1, and we've got 1 over 9 to the power of 2, and then here it's 4 to the power of 2 and 1 over 9 to the power of 3, and that continues on in general. So in general we have 4 to the power of n minus 2 times 1 over 9 to the power of n minus 1. So if we multiply through by 4 over 4, we can make those indices the same. So what we get then is AN is going to equal 3 times root 3 times s squared over, and times the denominator by 4. So we're going to get 16, and then we'll times every term in the bracket by 4. So we get 4 over 3 plus 4 over 9 plus 4 squared times 1 over 9 squared plus 4 cubed times 1 over 9 cubed, and plus 4 to the power of n minus 1 times 1 over 9 to the power of n minus 1. So we can write this as AN is going to be equal to 3 times root 3 times s squared over 16, and then in the brackets we have 4 over 3 plus 4 over 9 plus 4 over 9 all squared plus 4 over 9 to the power of 3, and it's going to carry on, and then the final term will be plus 4 over 9 to the power of n minus 1. So we can write this part out here using sum notation. So what we'll have then is AN is going to equal 3 times root 3 times s squared over 16, and then in the brackets we're going to have 4 over 3 plus the sum going from k equals 2 to k equals n of 4 over 9 to the power of k minus 1. So this part here and then this part in the line previous are just exactly the same. So for example, our first term here is when we plug in k equals 2, so we get 4 over 9 to the power of 2 minus 1, which is just 4 over 9 to the power of 1, and that's just 4 over 9. And then we're going to just keep adding 1 to the power as we go along in our summation. So the next term would be plus 4 over 9 squared plus 4 over 9 cubed, and then our final term we're going to have is when k is equal to n, so that would be the final term that we see here, which is 4 over 9 to the power of n minus 1. So now we're going to take the limit as n goes to infinity of AN. So we have then the limit as n goes to infinity of AN is equal to 3 times square root of 3 times s squared over 16, and then in the brackets we have 4 over 3 plus the sum, and our sum is going to go from n equals 2 to infinity because we've taken the limit as n is going to infinity, and then we're going to have 4 over 9 to the power of n minus 1. So we've just renamed this summation indice here as n instead of k, which you had in the previous line, just to make it clear that we're going from n equals 2 and we're taking the limit as n goes to infinity, so that's why I've got that sum going up to infinity. But the first term is going to be the same, it's going to be 4 over 9, and then we're going to have plus 4 over 9 squared. So the only difference is in this summation here, we're going to have an infinite number of terms. So we can recognize this term here, which was the sum going from n equals 2 to infinity of 4 over 9 to the power of n minus 1, is an infinite geometric series with common ratio r equals 4 over 9. Now, as the absolute value of r, well, it's going to just equal 4 over 9 because r is positive. So the absolute value of r is equal to 4 over 9, which is less than 1. We can find the sum of this infinite geometric series. So the sum to infinity is given by a over 1 minus r, where a is the first term of our series and r is the common ratio. So if we look at our geometric series over here, to find the first term, we just plug in n equals 2. So we'll get 4 over 9 to the power of 2 minus 1, which is just 4 over 9 to the power of 1. So our first term is 4 over 9. So we have then that a is equal to 4 over 9, and we know that our common ratio r is also equal to 4 over 9. So what we're going to have then is our sum going from n equals 2 to infinity of 4 over 9 to the power of n minus 1 is going to be equal to 4 over 9 over 1 minus 4 over 9. So that is equal to 4 over 9 over 5 over 9, and the 9's will just cancel, and that is going to equal 4 over 5. So we now have then that the limit as n goes to infinity of an is equal to 3 times root 3 times s squared over 16, and then in the brackets we're going to have 4 over 3 plus 4 over 5, and that is equal to 3 times root 3 times s squared over 16, and then finding a common denominator, we're going to have 20 over 15 plus 12 over 15, so that equals 3 times root 3 times s squared over 16 times 32 over 15. Now this 32 and 16 cancel, so we're left with 2 in the numerator and 3 over 15, well that's equivalent to 1 over 5. So this is going to equal then 2 over 5 times root 3 times s squared. So we're almost done now. We know that a1 was equal to root 3 over 4 times s squared, and we just found out that the limit as n goes to infinity of an is equal to 2 over 5 times root 3 times s squared. So what we'll do now is take a1 and show that there is some number that we can multiply it by, so we'll call that number x for now, and that is going to equal the limit as n tends to infinity of an. And in fact, we want to show that that number x is equal to 8 over 5. So we get then that root 3 over 4 times s squared times x is equal to 2 over 5 times root 3 times s squared. So we know that that s squared term is not equal to 0 because s is the length of a side, so s is definitely going to be greater than 0. So we can cancel out the s squareds, and we can cancel out these root 3's, and then if we multiply both sides through by 4, then we're going to get that x is equal to 8 over 5. So this means then that 8 over 5 times a1 is equal to the limit as n goes to infinity of an, and that's what we wanted to show. So we can just note at this step here, we could have just multiplied this a1 term here by 8 over 5 and shown that it was equal to this 2 over 5 times square root of 3 times s squared. But we just went through it a bit more thoroughly just to show that even if we didn't know that it was 8 over 5 times a1 that was equal to the limit as n goes to infinity of an, it was fairly straightforward to work out that that number was in fact 8 over 5. So therefore, regardless of the length of the sides we begin with, the limit as n goes to infinity of an is equal to 8 over 5 times the area enclosed by the first curve. So that shows that the area is in fact finite as n tends toward infinity, and we've shown previously that the perimeter, or the length of the curve, is in fact infinite.